I'm Brandon Lewis, aka Techie Lou, and I'm here with Umesh Lokhande. Say hi, Umesh.
Hi, everyone.
Great. So today what we're going to be, oh, it looks like we've got some internet things. Yep. All right. Looks like my connection's been restored. Sorry about that. So hi, everybody. I'm Brandon Lewis, aka Techie Lou, and we're here with another DevHeads Engineering Hour. And today what we're going to be doing is going over Modbus Master-Slave firmware on an STM32. And just give me a moment as I'm trying to set up a connection with the Discord server. If you are not a member of the DevHeads Discord server and as a member of the DevHeads Discord community, feel free to go check us out. We are over there on discord.gg / DevHeads. So one moment, guys, while I get the windows all set up. Let's see. And if you are over in the Discord, let me know if you can see the stream. But we'll go ahead and get started here. What we're going to be doing today is an engineering hour session, which is really a hands-on session during which Umesh is going to be walking us through the second part of a series that's already begun on Modbus. So we're really excited to get that going. And in order for us to have the best streaming experience possible, today, what we're going to be going through is 45 minutes worth of presentation, which is followed by about 10 or 15 minutes, hopefully, of Q&A at the end of the hour. For those of you over on Discord, just give me a second. I'll fix up that stream here in a bit. But for those of you in the rest of the audience, what you're going to want to do if you run into viewing challenges is take a couple of self-help tips. If you're in the webinar platform, there's a help button in the bottom left that's sort of a wizard. It'll walk you through a bunch of different steps that you can take to get your stream back on track. Otherwise, you might want to check your bandwidth. That's a common problem. If you are streaming below 5 megabits per second download speed, you may experience problems. So go to some place like speedtest.net and see how much you are pulling down. And if it's under 5, see if you can get on another network. Another thing that you might want to try is to get into stop using any applications that are not browser based. So if you are using the Discord app, for example, you might want to try the Discord browser version. A lot of times there are issues related to that. Close anything else that may be consuming bandwidth, close any other applications that may be consuming a lot of memory. And then other than that, if you do have problems, just DM me, either Brandon Lewis or Techie Lou, in whatever platform it is you're using, and I'll jump over there and see if I can help out and get you on track. So I don't want to take up much more time with a bunch of administrative stuff. I am going to be dropping links into the previous sessions, as well as to the Discord server, into all of the chat functions of the various platforms we're on today. So you will be able to participate with the community. We also encourage that you chat wherever you are, ask questions, and we'll pass them back to Umesh at the end of the hour so that you can get some of your questions answered. But like I said, don't want to take up too much time. I'm going to hand it over to Umesh. Umesh, take it away.
Hi, everyone. I hope you're excited to learn about Modbus RTU. And today we will be implementing the firmware for master-slave implementation, especially with a master to communicate with a multiple slave. And we will be using an STM32 microcontroller, which is ARM Cortex-M4 core. So we're going to start off with an overview. So we're going to put the foundation for how the master will be talking to a multiple slave and why it's significant for us to know, because in the previous engineering hour episode, we just have communicated simply Modbus simulator to talk to the STM32. Now we have to take it to the next level. So we want to connect a multiple slave devices to Modbus master. So we'll put things in perspective, and then from there we will carry on. And then we will discuss about the circuit connection, especially the wiring, because when we connect a multiple slave devices with the Modbus, we have to connect them in a multi-drop fashion. And I'm going to discuss like how you connect with one master and two slave with STM32 microcontroller. And then we will discuss the Modbus master firmware. Apart from the Modbus protocol itself, what are the things that we need to take care in order to make this communication works. I mean, I will be presenting a use case basically, and on the top of that use case, we will discuss the firmware development. And then we will dive into the Modbus slave firmware, because there will be a two slave Modbus slave devices. We will have to write an application layer, and we will discuss that how this application layer will be written. And then all these things will be backed by a live demo where I will be implementing Modbus RTU master and slave communication, multiple slave with STM32. And then we'll summarize all the things that we have seen so far. And towards the end of the session, I will take your questions if there are any. And if we run out of a time, then feel free to drop your question into the Discord server. We have a dedicated channel there, Field Pass. So this is what we will be looking into. So why we need one master to talk to multiple slave, and why it is significant in Modbus communication, especially Modbus RTU we are talking about. So when we use Modbus RTU, we have the ability that we can have a single controller that can manage multiple devices. So having one Modbus master can manage multiple slave devices. And this is significant because we can achieve scalability for multi-device communication. And we, if you remember from the previous session, uh, we have a device addressing. That means every slave device has a dedicated device ID. And in the Modbus communication, the master keeps polling. So this device addressing and polling mechanism make it scalable so that multiple devices can communicate, and you can create a network of the devices. So if you look at the industrial applications where you need to connect the multiple devices together and create a network of the devices for controlling or monitoring. Now in Modbus RTU, uh, using this Modbus RTU, it provides the interoperability between multiple Modbus devices because it's so popular and it's pretty old now. So building any solution that allows you to do a Modbus communication will give you a freedom that it will be very easily interoperable, so you can configure with any other devices in the multiple Modbus devices fashion. Then ease of integration, because it is widely adopted by many manufacturers. So you can see a lot of different devices like PLC, VFDs, transmitters. So if you build anything that can be easily be integrated with the existing system, uh, so it has its own significance in this way. Then the Modbus RTU is efficient and reliable, and this is made by its deterministic response and have a robust error checking mechanism. What does this mean? This means that whenever we have a master and slave communication, when the Modbus master is talking to multiple slave, the Modbus master would basically be polling all the devices, slave devices. And because the Modbus master is polling, the polling rate is basically being controlled by a master device. So you have a deterministic response that you can expect from the slave devices. And because the Modbus has implemented the robust error checking mechanism by implementing the exception codes. If you remember from the previous session, we talked about it, like to avoid the error in the communication, you can implement different exception codes in your firmware so that you can have a better error checking mechanism. And if you use a Modbus, even when you connect the multiple slave devices with an RS485 as a physical layer, you can have a several 100 meters of communication you can even achieve, and you can achieve this with a better noise immunity. So one of the reason the Modbus to be used with RS485, and that's the use case we also will be focusing on today by using MAX 485 TTL to RS485 converter, we can not only drive for longer distance the data communication, but the drop, the error into the data frame will be reduced because it's very uh, better noise immunity that you can achieve with this communication with RS485. I mean, the one reason that you have the Modbus RTU is to get along with the RS485 as a physical layer. Now, let's just talk about how it will be implemented on the higher level, especially one master that talks to multiple slave. So you can see here on the slide, we have the Modbus master, and this Modbus master has an STM32 as the microcontroller. And this microcontroller is talking to this MAX 485, which is which is MAX 485 TTL to RS 485 converter. And then this microcontroller is also have connectivity to the RTC module, so it can read the real-time uh, RTC parameters like day, dates, time, hour, minutes, something. And then we have the display, OLED display that we have connected. So when we put together everything, that means an STM32 microcontroller, MAX 485 chip for the connectivity, RTC module, and OLED display all together will form a Modbus master for us. And then this Modbus master is talking to two slave devices. So the slave one and slave two. So slave one again is same like the master. So it also has the STM32 microcontroller. Then it has its own dedicated MAX 485 TTL to RS 485 converter, RTC module. Now you might say, okay, the STM32 has a built-in RTC. Why are we connecting external RTC over I2C communication? I think the reason I used it because I just wanted to make a test with the RTC drift. That's in itself is a big topic to discuss, RTC drift, but having the accuracy of a nanoseconds, I needed to have something more robust with an external crystal, and this STM32 board doesn't have the external crystal on board, so I used an external RTC. So we have this slave device, which is same like a master. It also has one switch that is connected to STM32. So there is one master and there are two slave. And the way it works is this one master and two slave share the same bus. That's the Modbus. That's how the communication works. That's how you can create this network of the devices. Now the question comes, how does master knows which slave to communicate? That's why every slave, let's say if we talk about the slave one, it has its own slave ID, that's slave ID 1, and slave 2 has its own slave ID 2. Okay, now look at this. Slave 2 has the switch connected to STM32 and slave 1 has a switch connected to STM32. Now, whenever the master wants to, master first send the request to the slave 1 because master is always broadcasting. And when we set the poll rate, the master is basically one who dictates the network. So the master will say, okay, I am interested to talk to slave 1. So it will send the request to the slave 1. And the way it understand the slave 1, because the master knows the slave ID, that's the 1. So if the master wants to talk to slave 2, master will send the request to slave 2 as a slave ID 2. So master can able to track in the network which exact slave device the master wants to talk to. And whenever the master sends the request to, let's say, slave 1, then whenever, let's say, somebody press the button on the slave 1, the slave 1 will then send the response back to the master that somebody pressed the button, so button event get fired. And then the moment we press the button, this RTC parameters will be logged. Okay, that will be stored. And this will be sent it to the master. So master know that when user pressed the button on the slave device 1. Similarly, when you press the switch that is connected to this STM32, then it will give the timestamp whenever the user press the switch onto the slave 2 to the master in the form of response. So I hope you get the point how the master can able to send the request to the slave device, and then slave device then send the request response back to the master, and that's how this communication works. The point that I wanted to make here, which is very important, is master dictates the network. So the master device when we write the firmware for the Modbus master, we set the parameter that when we want to poll to slave 1. So let's say if you set the polling rate 200 milliseconds, so whenever, let's say, somebody press the event 200 milliseconds, the response will be sent it back to the master. Okay, then let's say if you send the poll rate for slave 2 to be, let's say, another 200 milliseconds, then so I hope you get the point. Like master, when we write the firmware for the master, then we write how how often we want to poll the slave devices, slave 1 and slave 2, and then which slave device to communicate with, that will be decided on to the slave ID, which is unique into the network. So it doesn't matter, like, if you remember, in one master can able to talk to almost around 32 slave devices. Okay, so because every slave device will have a unique slave ID, master can able to talk to that particular slave. I hope this makes sense, how master can talk to multiple slave. And there are two concepts very important. One is a slave ID and second one is a polling rate. And the poll rate is decided, I mean, that will be into the firmware of the master. Now let's go ahead, because in this project we want the STM32, when we implement the Modbus RTU firmware, it has to talk to other slave device with the Modbus, and Modbus to be used with RS485 communication. We will be using this converter, which is very, very popular. It's called MAX 485 TTL to RS485 converter. Now, the way this module will be used is the left side of this module will be a TTL signal, so that will connect to the microcontroller, and the right side of the pin will connect to another RS485 device, right? So that will be, let's say, our slave or the Modbus master device. Now let's just understand the pins onto this module. So you see on the left side there is an RO and DI pin. So RO stands for receiver output and DI stands for the driver input. So this RO and DI pin will be connected to the UART pin of the microcontroller. When we use this MAX 485 converter with the microcontroller, this side of the pin, TDL side of the pin, will connect to the microcontroller, and this will connect to UART. Because if you remember from the past engineering hour episode, we implemented the Modbus protocol onto the STM32, but then for serial communication we use a UART for that matter. And that's why here again, when we want to connect to the microcontroller, we have to connect to the UART pin. And then there are two pins like DE and RE. So RE stands for receiver enable and DE stands for driver enable. Now these two pins will connect to any GPIO pin of the microcontroller. Now you might wonder, what is the role of this DE and RE pin? So the way we configure whether we make a logic high and logic low, that decides whether this Modbus device wants to transmit or receive the data. So it basically decides the direction of the data flow. Okay, so let me just show you. If you set the DENRE pin, DENRE pin, which will connect to the microcontroller's GPIO pin. So when we write the firmware, if we set it to 1, then this Modbus device will transmit the data. And if we turn the GPIO DENRE connected GPIO pin to be logic low, then this Modbus device will receive the data. I hope now you get the point. Like this RO and DI connect to UART, from where to get the data out and in, and then the direction will be decided on DENRE. Okay, and on the right side where it connects to the other Modbus device, other RS485 device, the 5 volt, the VCC connects to 5 volt, because this module is the input voltage of this module is 5 volt, and the ground will connect to ground, and there is a line A and line B. These are the signal that will be used in RS485 to connect to the other device, right? So that's how you can use this max TTL to RS485 converter. And in the next slide, I'm going to show you how you can connect to the actual microcontroller and then how you can use it. But just as more information about this converter uh, module, the input voltage is 5 volt. The output is RS485 differential signal. This is very important. So this line A and line B, these are the signal which are a differential signal. That's why in the first slide, when I was talking about the significance of using the Modbus RTU for the longer distance to communicate between two devices, because this line A and line B will be a differential pair. It can able to transmit for longer distances, wherein it can manage to reduce the noise onto the line when you drive the data for longer distances. And also one more thing that you should know is this converter is a half duplex. That's why you can either transmit or you can receive at a time. That's why DENRE, when you drive one, it will transmit. So either you are transmitting or you're receiving at the time. So that's it. Now let's just talk about the connection. When you connect this max 485 TTL converter to RS485 to a real microcontroller, how it connects. Look at this. This is one Modbus master device. So the RO and DI is connected to TX and RX pin. These are the TX and RX pin of the nuclear board. And this RE and DE is connected to this GPIO pin, right? The other side, we have another Modbus slave device, and the other slave device is the other STM32 nuclear board and has its own max 485 converter. And the way this both Modbus master and Modbus slave share the data between them is by connecting line A of the master connect to the line A of the slave, and line B of the master will connect to line B of the slave. Now note this, even though this drawn just like a transceiver communication, it's not a transceiver. The line A connect to line A and line B will connect to line B. In RS232, it's something in the form of transceiver. RX connects to TX. That's not a case because we are using here RS485 communication. And because this communication RS485, as we spoke in the previous slide, that this uses a differential pair, you can literally drive your communication on a longer distance, several hundred meters, say for example. So this is very basic form of communication you can establish between a Modbus master and the Modbus slave. Now, this picture shows how exactly the setup is done at my site. And you can see here I have the STM32 nuclear board, and this will be used as a master, and it has its own max 485 converter. And then there is a slave one, so there's only one master and there are two slaves. So this breadboard is slave one and this second breadboard will be a slave two. Now, if you look at the slave one, then the slave one has its own dedicated max 485 converter. Similarly, slave two has its own max 485 converter with STM32. That's the same thing that we have seen in the previous slide, where I had one Modbus master that talks to two Modbus slave devices. Now, let's just understand how this master and slave is connected to each other. So look at this terminal block. So this is a line A and line B. So the pin goes through Modbus master. It will connect to the line A and line B of this slave one. And then from the terminal block, you can see this red and black wire will be taken out, and then it goes to the line A and line B of slave 2. Now, because the VCC and ground requires a 5 volt and ground, it will be taken from the breadboard itself. I hope this connection is clear for you, like how the master is talking to slave 1, and from slave 1 the connection of line A and line B is extended to slave 2. And similarly, you can add as many Modbus slave devices as you want. I mean, up to 32, right? With one master. So another thing is, I want you to note that on the Modbus slave 1, we have one switch connected to this STM32 board. And similarly, slave 2 has this switch connected. So what we want to test is, whenever we press the switch onto the slave Modbus slave device, so this is our Modbus slave device, all breadboard, complete breadboard. And when we press the switch on the slave 1, then it will basically fire the event, and then it will record the timestamp RTC data at what exact time the switch is pressed onto the slave device. Similarly, on slave 2, we have the switch connected to this STM32. Again, if somebody press the switch on slave 2, it will capture the RTC data. Now, when the Modbus master wants to talk to slave 1 or slave 2, the Modbus master will send the request to the slave 1 by calling to the slave ID 1, because Modbus master knows which slave it wants to talk to. So let's say first, in the Modbus master firmware, we write 200 milliseconds that the Modbus master wants to poll. So whenever somebody press the button, it capture the RTC value, because this is the RTC connected to this STM32. So the RTC value will be sent, I mean, not sent, but it is in the form of response back to the master. So master sent the request to the slave 1 by calling to slave ID 1 of slave 1. And then slave 1 will respond to the master uh, in the form of the response back. And then that timestamp, whenever the switch is pressed, will be printed onto the OLED for the switch 1. Similarly, if we press the button on slave 2, so this button, so another 200 milliseconds, say for example, the Modbus master poll to slave 2 this time, then slave 2 will respond back to the master's request the timestamp when the button is pressed. I hope this makes sense. Like in this project, we are basically press the button onto the slave device, and the moment we press the button, we record the RTC value, that what exact time the switch is pressed, and that data will be sent it to the master. So master basically record the both data from the slave 1 and slave 2 live in a real time. Okay, so this is the project, and it will be very interesting to see live in action how it works. I will try to show you on to the serial monitor, and then also onto the live on the LCD. So this is how our firmware implementation will be. So we would basically will write one Modbus master firmware. So one project will be for the Modbus master, and the other project that we want to write, so there will be a two project today. So that project will be a Modbus slave. Okay, for third slave 2, we don't have to write any special project, because we will use the same code, just we will change the slave ID. Because here in slave 1, we will have the slave ID 1, wherein for slave 2, Modbus slave 2, the slave ID only be changed. So I hope this makes sense how this firmware implementation will happen to achieve the one master, Modbus master, to talk to two Modbus slave devices. So let's just talk about the Modbus master firmware. Now, you might say the Modbus protocol is pretty standard, and you can use even some libraries, Modbus libraries out there, because Modbus is very popular protocol and it's very lively protocol even in 2025. So what special thing that we are writing? So we here talking about what application that we want to implement on the top of the standard protocol functions. So the Modbus master firmware in our project first read the RTC time on serial monitor, because whenever you build any product, even take an example of your computer. So when you used to buy a computer 10 years back or maybe 20 years back, the first thing when you power on your computer is you set the time, date, and country. I hope you remember. In today's world, we don't need to set the time and date because every other device like computer or laptop connects to internet all the time. So when we buy computer or the laptop, the first thing we do is we connect to internet. So moment you connect to internet, it will pull the data from internet and it will update. But several years back, but when you build the product, you still have to, if it's not an IoT, let's assume for some time. And if it's IoT, then you have a several network, several protocol which can pull the data. So because in this project, we don't have any internet connectivity, we will first read the RTC time. Read means we are reading from the external RTC. And then we are writing into the registers or the RTC of an internal RTC, right? So we are reading from external RTC, writing into the RTC value of the internal RTC. Now, you might ask this question, why are you doing this? And again, the point here is, if you have built any product, then, and if you have used RTC, because RTC is used pretty much in every other product, there is something that called drift been added when your RTC is not accurate, right? And because as I said, this nuclear board that I'm using is such a tiny little nuclear board, it doesn't have any pads that I can solder the external crystal. So I have to use an external RTC and then I can write the data. So at least using external RTC, I can able to synchronize the accurate timing of an internal RTC. Then, because the Modbus master is always in a broadcasting mode, every 1 second, the Modbus master will write into the RTC register. So to avoid the drift, we will always have the most accurate RTC parameters, because that's the timestamp that we are analyzing event. And in real-time system, timing is everything. If you mismatch the timing, anything that you try to do, whether it's a control or a monitor, doesn't make sense. So it's very important. And in the Modbus master firmware, we will pull the switch every 200 milliseconds from slave 1. So when we mention into the Modbus firmware itself, then pull the switch status every 600 milliseconds from slave 2. In the code, maybe we can put the same poll rate, 200 milliseconds, but if you want, you can change the different poll rate. It doesn't matter. And then we want to show the exact RTC value, the timing, onto our OLED display. And of course, then onto OLED display, on the first line, we will show, means we will display the slave 1 event timestamp. So when somebody press the button on slave 1, then it will be updated the event 1. And when somebody press the button on slave 2, so slave 2 event get fired, so the timestamp will be displayed again onto the OLED display that is connected to the Modbus master. I hope this is not super complex. By the way, if this looks complex, then this is pretty close to industrial application, right? I am implementing this use case for real projects. It's not LED blinking project. Now, when we talk about the Modbus slave firmware, because we have only one STM32 microcontroller, that will be Modbus master, and there's a Modbus slave device, so there will be two slave devices, so we have to write the firmware for slave as well. In the Modbus slave firmware, we will have 8 Modbus register to receive the time from the master. So because we know that there will be year, date, day, date, hours, minutes, all this parameter, RTC parameters. I hope every embedded engineer know. So we need 8 registers for these parameters, RTC parameters, that we will be storing into the holding register. And there will be one discrete input that we want to use for a switch status, because there will be a switch connected to the Modbus slave that when we press, the event get fired, and then the RTC parameter will be sent it to the Modbus master. So the holding register, then the discrete input, this is what we have to mention into the firmware when we write the microcontroller firmware. And I'm telling you high level stuff. So when we look at the code, then probably you will understand in more abstract way. So whenever the switch is pressed, it's capture the status in a discrete input. Okay, and then it will, as I said, display the time on OLED display, because the slave also has the OLED display of it. Then the switch event will be locked, and it will be sent it to Modbus master if the Modbus master send us the request. So response gets back to the Modbus master that somebody has pressed the button, switch is pressed, that's why the event get fired. And then the status will be updated, switch status will be updated, and the RTC parameters, the exact time will be sent it to the master. So master knows when the switch is got pressed. Okay, now here we are talking about switch, but switch can be any wall in industry, right? So somebody turn on and turn off the wall, and you want to monitor the wall status, right? I took switch because it's still easy to show me switch onto the live stream and uh, as compared to the wall. So that's how we will write the Modbus master and slave firmware. So let me just take you to the code and look at this. Here we have two projects into the STM32Cube Modbus master and Modbus slave. So Modbus master code we will first look at. Let me just open Modbus master. And as I said, we need only one Modbus slave, because we will upload the same code with just changing the slave ID for the slave 2, right? So in the Modbus master code, if you expand this project, this is very, very crazy. So I have not used any library, by the way, and I kind of have regret later. But because I didn't use the library, it's become very complex. So in the Modbus master firmware, if you look at the main.c file, there's literally nothing, because we are using a FreeRTOS. So you can see FreeRTOS. On the top of everything, I added the complexity in the project by adding the FreeRTOS, because I thought maybe using FreeRTOS would make the solution more robust when you communicate multiple slave devices. And the whole reason why we do this project is to analyze the response, the event responses, how great, how reliable, how flawless the communication happens between master and slave, that master doesn't miss any data. That's the whole objective when you compare with the other communication protocol like CAN or something. But anyways, because we used a FreeRTOS, you can see there is a file that I have written. It's called freertos.c file. So this is an application layer. In this application layer, we have to write everything that we want this Modbus master to do. And if I have to tell you in short, the one thing that you must know is all the devices in the network should have a same baud rate. So Modbus RTU baud rate, I set it 115200. Now, if somebody doesn't know, then because how can you decide which baud rate to set up? And depending on baud rate, everything change, like your RTU silence time will change. A lot of different timings will change. So usually you use higher baud rate like 1150-200 when your devices are very close to each other. I mean, very in the sense not too far. So I mean, usually it's a practice like 9600 is a baud rate people use as the lower end when you want to communicate over very significant uh, distance of communication. So the higher baud rate you can use for the devices which are closer to each other. That's how you choose in industry. And then of course you can play a little bit around, because you should know exactly how long you want to drive the data, whether you want to drive 60 meters, 150 meters, whatever. And then there is a silence time. uh, I mean, you can calculate this collector delay, which can be called. Then the most important part is there are three tasks. So one is the LCD handler task, there's a Modbus slave task, and there is a console task. There are three tasks in the project. So the Modbus slave task handles actual operation that we want this application to do, right? So the Modbus master, the role of the master is to poll the devices, right? So it sends the request to the slave, and then when the slave sends the response, then it listens. And by the way, it's always in a broadcasting mode. So the LCD handler task will take care of the data that is shown on the OLED display, and console task takes care on the UART. By the way, in this application, we are using two UART. So UART 1 handle the communication of a Modbus, and UART 2 will be used for the debugging and printing. Okay, and I set up different debug levels so that we can have a better visibility. I actually don't have that much time to get into every other part of it, because the firmware itself is complex to discuss. But I hope now at least you know. So let's directly jump into this task, Modbus slave task. And you might then say, okay, if this is a project of Modbus master, why the name is Modbus slave task? Because uh, first I thought maybe I would have only one project, and in the one project I will change a parameters, and that way I would handle. But then I ended up creating two different projects, so it just doesn't matter. So let's find the function, and you can see here is the task, and the slave poll rate. Remember, I said the Modbus master's responsibility is to poll the devices, and this 200 is the 200 milliseconds by which we want to poll the slave 1, and let's say for slave 2 we again want to poll it to 200 milliseconds, right? And then this is that logic that I have explained, uh, RS485 transmit. When I hover over, you can see the logic. So when you set the DENRE pin, when you set the pin, that means your max 485 will transmit the data from the Modbus, and then you send the data, and then you again reset back your pins to 0. That means you want again to go back your Modbus slave to be a listening mode, right? Oh, I hope I'm not confusing everybody, but this is just focus on this 200 milliseconds, which is a poll rate. So we are basically polling, and then you can see scan master is the function, and this one that we pass, it's the slave ID. So when this function executes, it reads the data coming from slave 1, and when this executes, then it reads the data from slave ID 2. That's how your Modbus master read the data coming from slave 1 and slave 2. Okay, I can quickly go into, so this is the firmware for Modbus master. And let me just close this project and go to Modbus slave project to, before I show you the demo. Again, this project is pretty much same like the previous one, because it's just the same thing. The important thing is when you upload the code on the slave Modbus slave device 1, you set this slave ID to be 1. And when you upload the same code slave ID for the second Modbus slave device, you can make it 2. That's how you set the slave ID into the Modbus slave device. And that's how the master knows the first 200 milliseconds when it polls the slave 1. The second 200 millisecond when it polls to slave 2, it's look for the slave ID 2, right? And then we need to have an holding registers. I mean, basically this project here, I created everything, all the memory maps from the Modbus protocol, but this will be used for the holding register for this RTC. Remember I said this, for RTC parameters you need the holding registers, and for the switch status we need, so this DI is a discrete input button status, and when I hover over, you can see, let me just hover over, you can see 10,001. If you remember from the previous Modbus episode, these are the addresses, that's where your registers are when you read the Modbus devices. And basically we write these parameters into this locations into the Modbus device. Like for holding register, it starts from 40,001 to 50,000. So this will be a 40,001, 40,002, 40,003, right? So it takes in a sequence because it's just like a pointer. So I hope now you know how this data will be handled. Now let's just jump back to the freeRTOS.c file, because that's the actual application implementation. Again, like the master, we have the baud rate as a 1150-200. All the devices should share the same baud rate. And then here into the Modbus slave task, again, there are 3 tasks here. So the one task that we should focus on, the Modbus slave task. So if I just find this, because we do not have that much time. This is, by the way, the complex firmware. So the Modbus task, you can see here, and here we initiate basically the RS485 signal that we want to transmit. Let me just take the key part, okay, like the slave callback and this slave callback. Maybe here somewhere there is a slave callback, you can see, right? And you can pass the register address and the number of register that you want to read. And let me just quickly go back to the part where we read the slave ID. So look at this way. Here we first have to check if the Modbus frame is ready. If the Modbus frame is ready, then it will check this, and then the request received. And then these are just UART based print commands. You may remember I said we are using 2 UART, UART1 and UART2. There are 2 UART into this nucleo board that we are using, STM32F303 nucleo board. And in this nucleo board, the UART1 is handling the data that is coming and going through the Modbus. So let me just scroll. So this basically console task, that's where we set the initial parameters. The point is this firmware is too big to explain to what to expect, because there are too many things. But if you wonder when I'm scrolling this code, that what is the set time, and then there will be a set date function here somewhere, set time, set date. These are the parameters that we can use from the serial monitor, because this console has to do with the serial monitor when we set the initial date and time RTC parameters. So what we were talking is that we set the slave ID, and based on the slave ID we transmit the data from our slave device, right? So UART stream buffer. So by the way, one more thing, like this UART2 buffer is a circular buffer that is implemented. And this RX buffer is basically to handle the RTC value, right? So whenever we upload this code onto the Modbus slave device, the slave device will assign the slave ID 1, and then it will start transmitting the data, I mean, in the form of response back to the Modbus master, because Modbus, let me just explain you in terms of the actual functioning. So if I just open device manager, I think we are running out of time. You can see there are 3 nuclear board are connected, right? I'm not sure if I can show you on the webcam, but here is the setup. So this one is a master device. These 2 are slave devices, slave 1 and slave 2. Let me just try to show you the demonstration on to the serial monitor. The reason I opened this device manager is because I wanted to show you the COM numbers. So the COM4 is basically is for the Modbus master, and then COM3 is for the slave 1, and COM9 is for slave 2. I know this because I've been testing it for some time, right? So you at least trust me. And it's complex because there are too many devices connected. So let me just open a cooldown, and I choose this application because I can open as many instances as I want, right? So in the other programs, it makes it very difficult to open and configure. So the first one, the first terminal, let me just configure, go to options, and the Modbus master is on COM4. And if you remember from the firmware, we have to set the baud rate 1150-200, click on OK, and then click on connect. So you see the Modbus master is basically working that, so it's polling our Modbus slave devices. So let me open another instance of the coolterm, and let me go configure the option. So let me just select COM3, which is a slave 1. The baud rate has to be same across all the Modbus devices in the network. So let's connect, and now you see the Modbus slave is also working. That means just printing some data. So I'm just trying to show you onto the camera in the webcam. So if I press the button, this is a slave 1, by the way. This is a slave 1. So when I press the button here, just let me disconnect for a second because this is too fast. The RTC, external RTC is too fast. And you see the log messages button state 1, and it record the timestamp. Okay, let me just connect back again. When I press the button, you can see it detect the press event. Now you see too many jumper wires, and I think it's better if I just hold it here and try to just show you. So I think the moment I hold it, it was so. Let's just reset. Okay, let me just stop, and now let me show you the output. So you see, this is a Modbus master. Okay, and look at this. It says data received from slave 1. And when we press the switch, it's logic low and logic high. Okay, press and release, right? The switch. Now look at the right side. That's a slave 1. And if I, because this runs very, very fast, you can see this was the event button state 1 pressed. Can you see? So this is the event that's been logged from slave to master. I can open the third terminal just for you to see. The slave 2 is on COM9, and I select the baud rate, and let me just connect all these terminals, right? So now look at this. This is the Modbus master. This is a Modbus master. This is slave 1, and this is a slave 2. Now I press the buttons here. Oh, again, if I hold it in my hand, this change. So let me just give me a second. This loose connection. Okay, you see, I pressed the slave 1 buttons couple of times and slave 2 buttons couple of times. Just a second. So let me just check. Slave 2 response. I got it. So let me just disconnect. Otherwise the screen will be filled of lot of data. Now look at this. When I press the button from slave 2, it receives the event from slave 2, right? And before, if I scroll up somewhere, you see the button data received from slave 1, right? And if you match the timestamp, we don't actually have a time, but if you can match the timestamp in the future, I am basically working on this case study where I am analyzing the event timings. This is very important in a real-time project. The moment you press the button and then you send it to maybe the time it reached to the Modbus master, still there will be a time that you elapsed, right? Even that time makes a lot of sense to consider when your device network is complex and you are handling data which you wish to be very accurate, right? A precision application. So I hope I'm not sure, but I can try and show the LCD. Can you see the LCD? Not sure if. Let me reset the master because I don't see myself. Reset the master. I can rather power off, but it's still very complex to show you all. So power off and power on. I'm not very hopeful because you see the first event parameter is 00 on the LCD. I'm not sure if you can see it's a 00. So the first one is a slave 1 here. So if I press this first button, the moment I hold this much circuit,
Can you lift it up any further?
Sorry?
Can you lift it up any further? It's just, yeah. There you go. Okay.
But when I hold this, is too loose, right?
I know.
It's impossible. I have to create it onto the actual PCB. And by the way, this sophisticated communication never be done like this. Okay. But I think this is the first multi-slave communication with the master on internet, I guess. Okay. So, but I think in the future we will have our own PCBs, small pieces. But the point here is that let me just power off and power on just to show people. Just give me a second. I have too many USB cables here. So now you see the master OLED display showing 2 events, right? 00. The first event is 00. The second is 00, right?
Mm-hmm.
Yeah. So when I press the switch on the slave 1, you see the first row is changed now. It has some parameters.
It's hard to see, but we'll take your word for it.
Okay, it's it's too complex. And slave 2 maybe, yeah, it's changed here. But yeah, I mean, you can, let me just run the, you see my screen? Now it's showing the logs on the serial monitor. Can you see?
Yeah.
Yeah. So now you can see the button. Let me press slave 2. You see, when I press the button, the master shows the data here. The button press status. Now I think something has moved along. Yeah, you can see that 2 status
Yeah.
when I
Yeah.
press the slave 2. Now let's test for slave 1. So on the top, this is a slave 1. So when I press the switch, let me move. Usually it's with the power, because if when anything that power disconnects, this ends up dysfunctional. You can see the slave 1. Look at this, right? The received from slave 1, right? When I press the slave 1's switch, right? So it does work. That's the best I can show you. So
Great.
let me just go back to the slides and just finish it. Actually, nothing much to finish, but just, so the advantage, it's with the Modbus RTU, it's still lively because it's a low cost, better noise immunity, scalable, up to 32 slave devices you can connect. I remember last time somebody asked, like, what if the maximum you can connect, and how will you decide how much you can connect? So the smarter engineer is, the more devices he can manage through the firmware. Okay, the average engineer can only be able to handle a couple of devices here and there. Okay, so so the maximum you can go to 32 to one master. Okay, now some people then come and ask this question: what if they use a repeater? Is it possible I can extend? Yes, you can extend through repeater, because there are repeater available. You can find out RS485 repeater that support Modbus RTU, and the best suited for monitoring devices in industrial application. One thing very important, it's a limitations, because why the other protocol exist, right? What are the limitations that the Modbus, at least to what I understand, what I have experienced in industry, I, I don't know everything in the world. So the limitation that I have realizes the continuous polling by master possesses a risk of timing mismatch. So we have seen that we set into the firmware where the Modbus in the broadcasting continuously poll the devices onto the network, all the slave devices. And when the timing mismatch happens, then there is a risk of losing data or losing response. And that's not what suitable for mission critical application, even in the automotive. That's why I believe the CAN is invented, right? The basic CAN. And from that, there will be CAN FD and other things. And then there are, again, so many other protocols, right? Yeah. So thank you very much for being a part of this 1 hour. And yeah, if you have any question, you can ask.
Cool. Yeah, we're a little over time, so not a lot of time for questions.
Yeah.
There was one there was one added here by Nadir. When a button is pressed over on slave 1 or slave 2, data is sent to the master over the Modbus. Why isn't data transferred from one slave to the other one? And Abdul just jumped in and said it's because slaves can't talk to each other. But I think I saw Rajasekar was trying to add a question as well, but it appears
Yeah.
maybe he dropped. Any closing thoughts, Umesh? Anything else that you like to add?
I think people can come into our server, and we have the field bus channel. And this is very interesting topic, because everybody in a community is working with such and scenarios, right? Different problem statements, because every industry, every solution that you build, even with using the same protocol, even Modbus RTU, everybody is trying to solve a different problems and different challenging and different way of implementing, right? So I appreciate if they come and they ask a question or they have some interesting thought on things which may be very interesting to discuss, right? And learn from it.
Yep, that's great. Well, thanks so much. Thanks so much. Oh, wait. Let's see. Uh, communication only works when disconnect the power plus VCC. Why?
No, it does work. I mean, it works flawlessly. Just look at how many jumper wires I have used. Can you see in a webcam?
Let's see.
Can you see on a webcam the setup?
Yep. Yep.
And when you have this many components, this is basically a kind of one product. You can have a little PCB. So that's why I kind of always checking in the power connectivity. Otherwise, it works fine. I mean, there's there's no problem with it. It works fine.
Okay. He's saying that it only works in his case, it works only when
Ah,
when you power pin.
okay. So in this case, when implementing the solution, the most of the time that I spent is with the timing. Okay,
Hmm.
so just make sure you set the character frame delay to be more than 3.5 characters. Okay,
Hmm.
and try not to use the equation or maybe a macro that is suggested by ChatGPT. Okay, because because I know many people go first and take the suggestion from ChatGPT, because the number that you set, that will depend on how much is your baud rate. So I don't know in your application, the code that you are writing, what baud rate that you are setting up. That's why I said it's okay, you can come into server and ask the question. In my case, you might have seen in the code, we used 115200 baud rate, and for that there is a 2 milliseconds, that the time that I have put in as a delay in between. I didn't use two timers basically to manage, but if you give enough time, right? Uh, I mean, try to experiment around it if you are not sure, because I don't know the baud rate and the other parameters. But just make sure the frame delay is set properly. Okay. And number two, you should, if you are using RTOS, by the way, then make sure the stack size is set up properly. Because
Hmm.
even though I was just, if you have seen my code, I am just handling three tasks. One task to handle display, one is for the UART, and the other one is for actual Modbus communication. But if you just set by default 256, which is basically the size, then it doesn't work. I found out that some functionality may work, may sometimes work, sometimes doesn't work, right? And then you have to reset, or maybe power off and power on, because power on and power off, you then reassign the memory, reset, free up some memory, and then, I mean, it's just, that's why you see sometimes it works, sometimes it doesn't work. So just make sure you allocate the stack properly, and then you set the frame delay good enough. I mean, if you set more, then it's fine, but it should not be less that you miss the characters in between, right? Some conditions.
All right, great. There was a question about which STM32 dev board was used. Which
Oh,
board?
it's used STM32F303. I can show you on slides. Look at this one, right? So this is the board, STM32F303. And I use this board because this is breadboard friendly, right? So
Mhm.
you can plug into breadboard. So I can create one Modbus RTU as a dedicated control device, right?
Mhm.
But then I end up learning, when I was writing the firmware, it doesn't have onboard oscillator. So I was then started having a problem, because I can't use internal RTC to to use with the external crystal, right? And without external crystal, your data, you don't get the highly accurate RTC parameters.
Yeah. Okay, great. Well, that's all the time we got today. Thanks so much, everybody, for attending. Yeah, we'll definitely see you in the community. And then Umesh is going to be working on some other field bus communication topics coming up here soon. So we're excited to get into some other protocols and potentially deeper into Modbus as well. So thanks a lot. Always appreciated, Umesh. It's always great stuff. And we will see you in the server.